Hello, my name is Tanner Dunn. I am a student at Cape Fear Community College. I'm getting my associates in engineering. I'm currently taking EGR214 Numerical Methods for Engineers, taught by Dr. H. Chapman. This is the spring of 2022. This is my semester project, and the related course we will be focusing on today is Physics 2. The topic we will be covering within Physics 2 is current resistance, more so RC circuits and solving for certain variables and functions within them. We will be referring to the textbook Physics for Scientists and Engineers with Modern Physics by Surway and Jewett. We will be referring to pages 726 through 729 of the textbook. RC circuits in the most simple manner are a circuit that is comprised of a battery, our EMF, which is our battery, a switch to disconnect the battery when we want to rely on the capacitor, and a resistor. This is the example we will be using for all the problems in today's manual. Now, relevant formulas we will be using from the text will be that initial current equals the EMF, or the voltage of the battery, over the resistance, which is in ohms, of the resistor. Max charge is the capacitance, which is measured in farads, times the EMF, which is measured in volts, or the capacitor times the battery. We will also be using a function for charge with respect to time, which is max charge times 1 minus e to the power of negative t over RC, which resistance times capacitance equals tau, our time constant. We'll also be referring to current as it equals EMF over resistance times e to the negative t over RC, or tau, time constant. We will be focusing more so on charging and discharging of capacitors when the battery is disconnected, which capacitors in a sense act somewhat like a small battery. They can build up charge and be discharged. So when a battery is disconnected, they still have charge in them and can run the circuit some until they are fully discharged. In this example, we are using those previously stated functions and equations and plugging in our resistance, which is 8 times 10 to the 5th ohms, and then our capacitance, which is 5 times 10 to the negative 6 farads, equals 4 seconds. And then our max charge equals capacitance times EMF, which is equal to 60 microcoulombs, which is the unit of measurement for charge. And then our current is 15 microamps. And then we plug these in to our functions of time to actually get, charge or current at any time. Now, for our first tutorial problem, we will be looking at an uncharged capacitor that was in the RC circuit as previously described, that basic one with the switch, the capacitor, the battery, and the resistor. And our battery has 9 volts, our EMF is 9. Our capacitor has a capacitance of 20 microfarads, and our resistor has a resistance of 100 ohms. Now, plugging in, we can see that, well, first we'll be solving for our tau, time constant, the maximum charge on the capacitor, and the charge on the battery with respect to time, when time is equal to 1 time constant. Plugging these values in, we get 0.002 seconds for our time constant tau, which is a Greek letter. For our max charge, we get 1.8 times 10 to the negative 4 coulombs. And then when we actually use our function for charge with respect to time, since we want it when t equals tau, that's really just e to the negative 1, which is 1 minus e to the negative 1 times 1.8 times 10 to the negative 4c, our max charge. And so we get a charge of 1.14 times 10 to the negative 4c. Now, for numerical or our MATLAB solution, we will be looking for Q, capital Q, which is max charge, and tau, our time constant, and then we'll be plugging our resistance, capacitance, and EMF. So our inputs, like I previously stated, are our resistance, capacitance, and our EMF. Our outputs would be our charge with respect to time, our max charge, and tau. Now, plugging in all these, we have a symbolic variable t. Our tau equals resistance times capacitance. Our max charge equals capacitance times EMF. And then we have our function for q with respect to time. Now, in this example, we are actually adding this extra line of dialogue. You wouldn't need this in most examples because we want to find when t equals tau. So, plugging all of that in, we can see that our time in seconds is 0.002, like previously stated. Our max charge is 1.8 times 10 to the negative 4 coulombs, and then approximately our charge is 1.14 times 10 to the negative 4. There was just some rounding error there. Now, for our second problem, we will be looking at a standard RC circuit. Tau is some constant. It can be any constant as long as it's not infinity or a negative, because tau cannot be negative since it's a time constant and we don't work in negative time. We will be using our max charge, and we'll be finding the charge of a capacitor at certain times, t equals 0, and as time approaches infinity. Now, for a capacitor that's not charged, logically speaking, at time equals 0, it has no time to charge, so it's going to equal 0. But as time approaches infinity, you have an infinite amount of time to charge that capacitor. So that means eventually it will reach its max charge as time goes on and on and on. Now for our function, we will be looking for charge. We will be labeling this as chargeCap2.m, and we did the same thing with the last file, but instead we changed that to a 1. Our inputs are tau and a, which a is just some variable that t approaches for a limit. So for our symbolic, we have max charge and t, tau, and so we actually plug in a expression where charge equals a limit for this function as t approaches some variable a, which a is one of our inputs. We could have just plugged this expression in here and then made this q. This charge here and this charge are the same. It just really depends on how MATLAB likes to process it, but we get the same answers like previously stated. At 0 time, there's no time to charge the capacitor, logically speaking, and then when time is infinite, it eventually reaches max charge capital Q, which makes sense logically also speaking. Now, learning to solve for different variables and functions and expressions that correlate to RC circuits is a useful base of knowledge. It identifies relations between these components and how certain variables can have a great change in the outcome. Capacitors and resistors are just a general big part of the 21st century, and they are in almost all the technology we use today. Knowing how these components work and the applications they can have can really strengthen not only your designs as engineers, but also being able to work together on teams from engineers of all disciplines. Through this manual, this base concept of RC circuits can be applied more efficiently through MATLAB, speeding up the processes of diagnosing certain outcomes and variables. There are a lot of other concepts not covered, like Kirchhoff's laws and loop rules, that can also be stacked on if you would want to. But those laws were not covered in the manual today. Thank you for your time and attention.